Welcome all of you to this last seminar of the fall 2022. We are extremely honored to have Professor Mingwei Chen from Johns Hopkins University, who's been there at the Hopkins Extreme Materials Institute and in the Department of Materials Engineering since 2017. I have had the honor of reading a lot of his papers. I also followed them for a number of years. And prior to Johns Hopkins, he was at the Tohoku University. And he has a whooping 500 peer-reviewed articles and has received 60,000 citations, which is amazing. His research focuses on the structure and property of advanced materials, particularly in the sector of energy materials and non-equilibrium and nanostructural materials. He is recognized internationally for his contributions in the area of metallic glasses, 3D nanoporous functional materials, and especially the shock-induced amorphization of armor ceramics. So with that, Professor Chen, the floor is all yours. Thank you for accepting our invite, and I look forward to your seminar.
Okay, thank you, Professor Anket, for the nice contribution, nice introduction. Actually, I'm really it's great honor. I'm the last speaker of this seminar series. So thank you everyone. So today, actually, I'm trying to talk about something, a little bit sounds strange, 3D graphene. So actually, a couple weeks ago, I have visited, come to my office, talked to me, said, "What are you doing, Mingwei?" I said, "I'm doing something 3D graphene." He said, "3D graphene is graphite." That's right. So if you vertically staking your the graphene, actually you make graphite. But what I'm talking about, this kind of 3D graphene today is something a little bit different. So actually, we are mainly come from three-dimensional constructed 3D structures. And you guys can see it here. So I acknowledge a couple of funny ideas from ASF and also some from Japan, because this program I present here, the most of the result is actually accumulated the last 10 years of work in my group. So many of my students, postdoctoral and research staff, they made a contribution. With those people, I cannot talk about 3D graphene today here. Okay. Let's start with my story here. So graphene is so popular, right? I need to say everyone knows. Actually, you see, for the paper publication, the number, I think just a couple of years ago, I met, the Nature Materials, the editor. He told me that they have the database. Highest publication number for the paper from the material science community is still the focus on the graphene. The simple reason, the graphene from the such material science engineering viewpoint, not physics, besides many magic physical property, the graphene material is basically sought after material, I said, for structural function application. The simple reason, high electric conductivity, right? We know the graphene, has high conducting material. Also mechanically, graphene, people call the strongest material. For theoretical strength, go to the the Pascal rather than gigapascal, right? It's much stronger than all the material knows. And also because it's 2D sheet, it's pretty flexible, right? More important things for many applications, the graphene has a large specific surface area. Somehow, as people reported 2,000 square meter per grain. So those are, of course, may not be as large as MOF, as the COF gives something 6,000 or 100,000, but 2,000 square meter per grain is really definitely the huge area. More important things, this large surface area material with highly electric conductivity, but also chemically stable. So that's what we know. For many our engineering material, they have large surface area, but their chemical stability is poor, right? But those kind of combination, have large surface area, high conductivity, high electrochemical chemical stability, definitely give a lot of promise for the structure and function application. But however, all those kind of sought after property, we talk about graphene, it comes from the perfect atomic thin, this the carbon nanosheet, right? But actually, in our real the world, when we use this material for device, we often need this so-called bulk material. At least, for example, we use all the electron in our battery supercapacitor, fuel cell, or many the biosensors. At least we need this the electron thickness or diameter, at least in the tens of micron or 100 micron level, right? think about these atomic layers in carbon with our tens of micron thickness requirement. There's a big gap in the line scale, right? So really get the application for this graphene material into our device, or the part of our machine, or the part of our, for example, car, or some the function such application, we do need construct graphene to the three-dimensional. The way basically naturally we can think about just we have a piece of paper is two-dimensional, but we can stack in the paper, get very thick, go three-dimensional, right? But just something we are repeat the nature's the idea to build up the graphite, but use use graphene sheet to reconstruct again. But this kind of vertical stacking is naturally introduced many issues. First, the isotropic in conductivity and magnetic property, right? Because those kind of restacking, actually, in most cases, just like two pieces of paper stacking together, you sometimes hard to separate it. Actually, you lost excess surface area. So that means, even graphene set have 2,000 square meter per gram, the surface area. But when you do the restacking, build up this kind of bulk sample, actually the accessible surface area get dramatically lost. So you lost at least one property for those kind of the light surface area. But also because the intersheet connect just like graphite. So you only had one wire interaction. So the conductivity, at least along the vertical direction, become very poor, right? For mechanical property also become isotropic. You cannot, the standing high stress along the vertical stacking direction, right? Also, from chemical, electrochemical viewpoint. So when you have this kind of stacking structure, you have a large, we call edge state, edge area. Those areas, the carbon atom no longer stable. So actually, if you do electrochemical measurement, you're going to see those edge atom prefer to be an oxidizer as a low over potential. Right? So those kind of strategy to restacking definitely it may work for some area, but not be universal for such application or function application of the graphene. Another idea to build up three-dimensional structure or the box structure to make this kind of the cellular structure. We form like the configuration. We know that we have the metal form, we have nickel, the zinc copper form available in the nature. Or can we make graphene in this kind of configuration? If you have this kind of configuration, you can have open porosity. All the surface could be accessible, right? You still can keep light surface area. Also, because those three-dimensional is random oriented for each ligament, you can introduce the isotropic property of graphene, right? Also, the larger porosity is going to give the large, the lighter weight. It's going to reduce the weight. It's going to make lighter weight, the graphene material. But also, this kind of three-dimensional continuous framework can for certain kind of mechanical property, mechanical stress to make the material flexible, particularly on the compression. Right? We have demonstrated this kind of configuration in many, the metal alloys, even the polymer, right? But how about the 2D material? With this kind of idea, in the last almost 10 years, you should see that through the literature search, many efforts have been developed by people from different areas. People develop so-called CVD to grow graphene into nickel template or copper template and dissolve those kind of nickel form to get freestanding porous the graphene. People do this kind of the coating. You can also coating in the graphene nanosheet into this the metal form and dissolve this metal form to get three-dimensional structure. People also do 3D printing, do this self-assembly, but many publication in the literature, at least I know hundreds of publications about the assembly or construction of 3D graphene by all those kind of techniques. But if you see their property reported by those materials, you're going to notice, actually, I cannot say, but most of these 3D constructed graphene, they are hard to keep this kind of 2D electron property. First, the conductivity become very poor. But second, this, the large accessible surface area get lost because, for example, you use nanosheet to reconstruct this one. Basically, your ligament size much thicker. So actually, you cannot keep the 1,000 square meter per gram, the light surface area. Also, mechanical property of flexibility of those kind of 2D, the graphene constructed 3D structure also become pretty poor. It's hard to compare, hard to compare with, the 2D, the property of graphene. So to preserve those kind of sought after 2D property and move this kind of property, keep this kind of property into 3-dimensional graphene structure, we need some, at least, the innovative material design idea, right? So we need to keep those kind of, graphene sheet in 3D structure have good contact. So we still have, to avoid the so-called pi binding, this kind of one-wire interaction or the edge interaction, right? To make the electron can smoothly flow in within this framework. But second, we need to put the quality of graphene nanosheet. We cannot use this kind of reduced graphene nanosheet as a fundamental structure building to construct 3D structure, because those graphene sheets are too defective, right? So also we need to construct this 3-dimensional structure has the property aspect ratio. That means the ligament thickness and the porosity have been optimized to make those materials can self-standing, can afford high strength and high force. Okay. So one idea come to our mind is actually we're trying to design this kind of configuration for 3-dimensional graphene. So basically it's bicontinuous. The nanoporous structure, all the graphene sheet interconnect in 3 dimensions. The pole channel is connected in 3 dimensions. As those structure basically, it's not the new for the material scientists or for mathematics. Basically, people know this kind of configuration for years. People call this kind of the Mingwei surface. Was first discovered back to 1863. It's one of the popular subjects in mathematics among mathematical community. So those material basically have this kind of configuration has pretty good the property come to this kind of the connectivity and the surface area, accessible surface area, and come to those kind of the structure, the stability. As a unique point, those kind of Mingwei surface all have the unique feature they call zero mean curvature. So any point, actually they have the both positive and negative curvature. The mathematical is magically the configuration is not only beautiful, actually come to the nature, the many the nature system pick up this kind of configuration. For example, we see beautiful color for our the butterfly, right? So for this beetle, the color for the skin surface. Use microscopy to see the inside structure. They all have this kind of Mingwei surface structure selected by the nature. Actually, for material science community, for ours, we also this kind of Mingwei surface structure is not rare. Actually, that can happen in the copolymer. And also can happen if you're familiar with kind of alloy decomposition or spinodal decomposition. All the structure basically the form also have this kind of Mingwei surface structure. The reason that nature lacks this kind of structure because those structure can minimize the surface energy. Yeah. So we are trying to get this kind of structure for graphene. We definitely first need looking for this kind of template. So one the template we are used for the de-alloying nanoproximity. So the de-alloying approach somehow just go opposite direction of alloy. We know most material alloys we use in our the daily life, which we call alloy because we put the second element, third element, you more into one simple element, simple element to use this kind of secondary, third, fourth element to strength to change the property, right? We call alloy. But the alloying process just go opposite way. So actually, the professor called the productivity at advanced state is one of the pioneer in this area actually. So people know this phenomenon for 100 years. It's actually a big concern in Christian science community because when we most of our alloys if used in the Christian atmosphere or environmental, actually you're going to get one element going to lost from this alloy that form this structure. The conventional alloy, this kind of reaction called de-alloying, leading to material they become brittle, right? Lost mechanical property. But I think in the last 20 years, the de-alloying community has spent a lot of effort basically make this kind of de-alloying approach become one powerful tool for nanofabrication. We can fabricate the nanostructured the porous material. Actually, essentially, those kind of porous material, if you do the three-dimensional reconstruction, you TM tomography, you're going to notice the actual structure is pretty interesting. This is why tomography structure for three-dimensional nanoporous good by chemical dealloying. So if you do this kind of culture analysis, you're going to notice actually those the inside culture for this metal ligament, actually they have mean surface feature. The mean culture, the positive culture, and negative culture, the mean with the balance point is always 0. So the mean culture is 0. This is a key feature of the mean surface. So those kind of mean surface basically we can get by the dealloying, right? That's pretty exciting. So because many of these kind of the 2D material, they can CVD growth or atomic layer growth into the metal substrate, because those kind of metal substrate can act as the catalyst and also as support. For example, in the nickel, we know is the best subject for the graphene growth, for hexagon boron nitride growth, right? So also for this the gold is good subject. For this the TMD, for example, molybdenum tungsten disulfide, tungsten selenide, those 2D material the growth the template. So now we can make this kind of three-dimensional nanoporous metal with this the mean surface structure. So we can directly utilize this kind of dealloying nanoporous metal as the template to the CVD growth. Right. So one example I'm showing here is actually for the graphene growth, we utilize this kind starting from nickel manganese foil with the thickness you can control from the 10 micron to 100 micron, the thicker. To dealloying, actually you get nanoporous nickel. You use nanoporous nickel as a template put into the CVD chamber to the CVD growth. You can growth the graphene on the internal surface within the deep channel, right? By the chemical aging, you dissolve and remove this nickel, you can simply get this kind of three-dimensional graphene. So if you move this sample to the microscope, you're going to see you have bi-continuous the porous structure fully adopted from this nanoporous nickel subject can be well resolved in the 2D graphene. This is one example here. So by this way, actually, we can construct the 2D graphene with the three-dimensional the structure. So as we know, this kind of nickel ligament basically have the mean surface feature. So those the 2D graphene actually they are inherited this kind of the mean surface structure, but keeping the 2D the features here. Those samples, because we grow by CVD, so they can be the pretty large size to direct get into the ball. For example, show one example here. We can get tens of centimeters diameter size of the sample with the thickness tone from 10 micron to 100 micron. So depending on your CVD system. You also can control this CVD growth condition, the temperature, time. So actually you can control get monolayer graphene, field layer graphene. So because those graphene will grow by CVD, so if you see the D band, basically the indicator of the defect of this graphene, basically the D band pretty weak. So they indicate those graphene have pretty good crystallinity, right? So those kind of high crystallinity and can be easily confirmed by electron diffraction. Bring the sample, come to TM, the machine TM, do the diffraction. You see you get sharp crystal-like diffraction peaks. Also, of course, you can do Hopkins TM. You can see the beautiful, the hexagon lattice of the graphene. We do see because those three-dimensional graphene, you have some area have a high criticality. You do see the elastic strand lattice from this electron diffraction, but Hopkins TM also can reveal. Sometimes you can see so-called topological defect called 5-7 is topological defect. Because those defects are generated when the graphene grows, because accommodate this kind of curvature. Because those samples is the three-dimensional in the bulk form, right? You can use your finger to pick up, hold the sample to whatever area, anywhere to do. So we can do this kind of mechanical testing just like the traditional in the metal sheet or this polymer sheet. You cut the dog bone shaped sample to the tensile, you got to pull the sample to tensile testing. So this is the stress strain curve. So actually, because when we do the CVD growth, we can control our graphene, the porosity and the layer, graphene layer thickness. In another way, we can control the density of 3D graphene. So we can convert, light graphene material, this, to the 3 milligram per cc. We can get a little bit heavy weight, come to something around 100 milligram per cc. So definitely, because we know the strength, depends on your density, right? Your light, the density, low density sample has a low, the tensile strength. Your high density sample definitely gives us, the high, the strength here, right? So actually, you can, this kind of correlation, density dependent in mechanical property can be simply characterized by conventional this tensile testing. But if you look at it close for this strength curve, you're going to notice basically those kind of, the sample with a low density somehow show this plastic-like deformation behavior, no longer filled by the linear deformation, right? For this kind of, the high density material, basically pull the high strength, just simply filled without any, indication for plastic deformation. But the light density, low density sample, somehow you're going to see those plastic deformation-like feature. Yeah. To deal with this kind of porous material for the, the comparable strength, the modulus, the how strong, how weaker, somehow you have to really consider the density. You have to do the scaling relation, use density to scale your strength. So you can plot it together to call the, density scaling, the mechanical property for the porous material. This is the result. We do the scaling, the density for the, the tensile strength series curve from this, strength. We know the density. We can plot this kind of, the scaling relations here. As you can see, actually, we also collect all the literature report the 3D graphene material from mechanical property, from different groups. So this, the 3D graphene grows by CVD with this surface structure show the highest, the strength among all the report of graphene material. But if you look at the, this kind of fitting, this kind of, the density with strength correlation, you're not going to find, if you use a single linear relation to fitting this, the scaling relation, you're going to find it, you're going to get big error bar. But if you separate this kind of, the fitting relation by the two regions, this low density region, high density region, you're going to find this fitting exponential relation, exponential number to change. For the high density area, actually exponential number something equal to 1. The M value, we call M value equal to 1. That means this is the porous structure, the deformation is mainly dominated by the strength model. So that gives the high strength, but somehow it's more brittle. But when you go to the low density region, you're going to see exponential number, basically 1.5. People know with this value means this deformation more likely by the bending. Okay. Those binding definitely is more flexible. So that means when we change the density, actually the deformation model for the 3D graphene will change from low density, the binding dominant deformation to the high density, the stretch dominant deformation. Actually, this is the consistent what we saw. This kind of somehow we can call the ductile to brittle transition. Okay. Besides these strengths, because you do the tensile tightening, you also can measure the modulus, right? You can scale the modulus. Actually, the modulus also, show this, among all the report graphene material, this material show the highest, the scaling modulus. So those models, if you do the scaling relation, also for compression and tension for our 3D graphene, they'll show this, the exponential number, something around 1.6. They're pretty close to, pure down the binding model. That means in the elastic deformation state for those the graphene sample, basically they are mainly dominated by binding. That's pretty reasonable because you have atomically thin the wall for this 3D temporal structure, right? When you apply the force with elastic deformation, is mainly carried out by those kind of binding elastic deformation. Yeah. So we can plot this kind of mechanical property to for comparison with all the known-based porous material, for example, the ceramic macrolattice. So you can see the graphene indeed our, the structure, we use atomic thin, the graphene, and, the building block and the beam to construct three-dimensional structure, but the overall property is comparable to those, the stronger ceramic, the microlattice. Because this material it has pretty good, the strength, ductility, flexibility. So basically, you can find, many structure application. One application I'm showing here is actually for the you can use this one, use graphene, this 3D bulk graphene sheet, make the device we call the thermal actuator. Basically, you can change the voltage, you change the current density, you change the temperature. Actually, you change the binding. So you can see you get a large binding, can repeat this kind of, the deformation process for hundreds of times. So that shows you the pretty good sensitivity to utilize this material for the structural function application. Right? And point actually, we are starting this design, this 3D graphene. We said we try to keep high, the electronic property of the 2D graphene. So one most famous, most important, the property, electronic property for the graphene is, they have the mass-free, the diagraphenia, right? The diagraphenia at the firm surface, the area, they're going to show linear dispersion. This is very known for the 2D graphene. These are 3D graphene. Basically, you will have the, three-dimensional construct structure here, but you still can keep this, it's a linear dispersion relation. But if you use, the airpath, we call angular, without this, for emission spectrum measurement here, but we lost the angle dependency. The two-dimensional graphene shows the strong angle dependency, but for our three-dimensional one, we cannot see the angle dependency. They're pretty simple because our sample become isotropic. All the graphene sheet in three-dimensional have all the random orientation, all the orientation can find graphene. So we no longer keep this kind of angle dependency. But they do have keep the kind of 2D electronic behavior. You still get the mass-free diagraphenia along the Fermi surface. That means this material still can give us very high conductivity. So those can be confirmed by our we call electric double layer transistor measurement. We build up this kind of electric double layer transistor, use our bulk graphene to make this device to measure the conductivity. Those this shadow region comes from all the literature report, the perfect 2D graphene, we call the transport property or mobility. These are 3D graphene. So in the low temperature, basically we are pretty close to the low bound of this perfect 2D graphene. That means our three-dimensional graphene still keep very high, electric conductivity. But definitely this kind of conductivity correlated with the pole size. We get the smaller pole size, something around 100 to 300 nanometer at high temperature, you're going to see the decreased electron mobility. That's pretty reasonable because you get a highly curved graphene, introduce additional effect. Those could be the topological defect, could be electron interaction. So they're going to change and increase the resistance. Okay, but overall, this material 3D graphene still has very good electron conductivity. So even the constructing, the constructing to the three-dimensional structure, right? So one application for those graphene material with high conductivity, large surface area, high mechanical flexibility. So one application for this kind of property is for the electromagnetic shielding. We know this day electromagnetic shielding becomes so important because everyone uses cell phone, right? Particularly go to 5G cell phone. Those electromagnetic, the radiation going to be pretty important, for the damage our health and affect, the surrounding other electronic devices, right? So developing new shielding material, actually, is pretty good, pretty important research area. So because our sample is bar, so we can directly use our box sample, just like the piece of paper, put into the device to do this kind of electromagnetic shielding measurement. Or you can conduct this measurement with the density dependency, signal dependency, the measure in a different frequency range. Actually, tend to be this our three-dimensional graphene is one of the best, the electromagnetic shielding material. The simple reason because high electrical conductivity, large surface area, those large surface area, internal surface area, can effectively reflect this kind of electromagnetic wave to enhance this kind of electromagnetic wave absorption, turn electromagnetic wave to a charge current, charge current. Those charge current at least recipient within the highly conductive graphene sheet, right? So can quickly decay those the electromagnetic radiation. So if we list our, we do the survey to, this is the five red star is, we call the EMR, the magnetic, the interference shielding efficiency. So actually our material is graphene is standing as one of the best material compared to, the metal, other carbon material, other 2D material. Also, those because graphene are, the graphene, 3D graphene is flexible. So we can do the, check this kind of frequency, shielding dependency with your deformation. When you come to the 30% stretch, actually, you see the shielding efficiency doesn't change too much until 60%. Probably introduce correct deformation, make this kind of shielding efficiency become decrease, become worse. But 30% flexibility are good enough for many flexible electronic device applications. Because the three-dimensional graphene has curved surface, right? So I have the, as I mentioned before, I have topological, the defective, this topological defect. Also, we closely sample from bottom up, growth by CVD. So we can naturally do chemical dot, right? We know the chemical dot is medical, the tool for from the scientists. So we can utilize chemical dotting to change the chemical physical property, right? So one application we are using is, to the nitrogen doping, sulfur doping, and phosphate doping to doping those, the foreign element into graphene light, 3D graphene lattice to change their property. This is this application. We do nitrogen doping. You do nitrogen doping, basically you can control the nitrogen doping concentration by control CVD temperature, control your precursor concentration, right? So this, the years chemical mapping per year show the nitrogen has been, doping into this graphene lattice. So definitely this distribution is not uniform in the three-dimensional graphene. Some in the area get a little bit high concentration in the nitrogen, because those areas have the high curvature, potentially have the, probably have the, high concentration of the topological defect. Yeah. So XPS measurement also confirm those, the nitrogen indeed doping into this, the carbon lattice to form this, the pyridine oxide, the graphic, the configuration to nitrogen dopings. With those kind of chemical doping graphene, we need to think about any catalytic application, right? So people know if you doping nitrogen into the carbon, basically you can turn the inert carbon into the ORR active carbon, like oxygen reduction reaction, right? So this actually we confirm this one in our three-dimensional graphene with surface structure here. So if not, this is without any doping the graphene sample. Actually, there the ORR inactive, but with the increased doping amount of the nitrogen, actually show this kind of increased ORR activity. So also based on this kind of local configuration characterization, we notice actually this kind of the ORR, the activity not only associated with the concentration of nitrogen, but also correlated with the configuration of nitrogen into the carbon graphene lattice. Besides this kind of direct chemical doping, we know because we can do the 3D growth, we can control our nanoparticle metal, the substrate, the size. So now we can tune this kind of nanoparticle structure from the micron scale, the porosity, come to the tens of nanometer. So what that means? That means when you get a smaller size, you get a heavily curved graphene. That means you can increase the density of this topological defect. When you do the chemical doping, those kind of high density the topological defect graphene definitely have opened many new operations to house the chemical dopings, right? So indeed, we noticed when we turn the pore size from something from micron to the tens of nanometer, this the foreign element doping concentration can be dramatically increased. Even we keep the same CVD growth condition. The simple because you get a curved graphene, you get more defective the structure. Now also when you change the curvature, basically you change the ratio of the log configuration of those chemical dopings within the graphene lattice. At least for those kinetic doping one, when you give this increase the curvature and decrease the pore size, we can enhance those N doping and P doping configuration, which could generate so-called the self-consistent electron donor, electron acceptor. So that's offers the highest catalytic activity, as we demonstrated here. This is for the hydrogen evaluation reaction. Actually called water splitting. This is one green way to produce the hydrogen. Yeah. Combined with this, the initial calculation, you notice actually this kind of doping plus this kind of enhanced log configuration actually can tune the reason. We can get this kind of doping with small curvature can enhance catalytic activity. The simple reason for this kind of doping can decrease the hydrogen absorption activation energy, make those values pretty close to the best non-noble measure of the PT, the catalyst. So that's the reason, actually, with this small curvature, with the optimized chemical doping configuration, with increased doping concentration, actually we can make this metal-free catalyst with performance pretty close to the noble measure of the PT. Right? Besides those kind of chemical doping, because the light surface area, let me see. Because the large surface area high conductivity also make this graphene, 3D graphene pretty, the appealing subject for, loading the single atom catalyst. One example shown here is we loading the nickel single atom catalyst into, this 3D graphene. For the single atom catalyst community, we know we face the challenge for increased loading amount, right? So you need to loading a large amount of single atom catalyst into this your support. But because graphene itself is a lightweight, light surface area, so we can dramatically increase the loading amount, given the high catalytic performance for those single atom catalyst. So those single atom catalyst behavior can be simply confirmed by this XPS measurement. You can see individual you never find a nickel-nickel bonding, only can see nickel carbon bonding. That means all the nickel isolated by surrounding the carbon. Also TM also can directly show the kind of the single atom feature of this nitrogen single atoms arc onto this graphene. So basically we do this kind of initial calculation. We also this kind of topological defect going to be strength this the interaction between nickel with graphene, getting enhanced this the catalytic activity. With those kind of the single atom the loading the 3D graphene with chemical doping graphene, actually those graphene from inert to show this kind of ORR, OER, HER property, particularly for the ORR and the OER. We know if you have bifunctional catalyst that can do the ORR, OER, the nature think about this material going to be good for application for the metal air battery. Right, this is one example. We use like this, the single atom anchor, this kind of 3D graphene with chemical doping for this think air battery measurement. So this actually this battery we use this one as a cathode. Basically show we do the comparison with traditional noble metal based anode cathode combined with those pair with our just chemical doping 3D graphene. The performance is so good. Particularly sucking stability is excellent. It's excellent. I don't have time to go to my details, but it's definitely this kind of bifunctional catalytic activity. It makes this 3D graphene the box form the electrode can be directly used as the electrode for the metal air battery. Also, you can use this one for the not only for thin-air battery, for the lithium-air battery. I don't know how many minutes left.
We still have about 15 minutes.
Okay, I'm really moving.
No.
I'm sorry about that. So actually, this is another application. You can pick up this kind of chemical doping in the graphene into in the console to build up this kind of, we call it the lithium-air battery. So again, those batteries show pretty good performance, and also by the chemical doping, you can tune the capacity or potential or silencability for those for these the batteries. Because the large surface area, you can do chemical doping. You can change you can load in this the metal like lithium metal into the inside of the channel to form this kind of the lithium metal anode, right? Large surface area with minimum local electrical density, they also prevent the dendrite growth. It's key challenging for this metal anode, right? Basically, they show the pretty good performance for the anode. We can combine this cathode and anode together, so we develop so-called graphene-based the pretty solid state lithium oxygen lithium-air battery. So that's actually the patent by the Toyota that shows excellent performance for the better applications. So I think I need to run up here. I have to stop here. So it's basically I want to give you some information in today's talk. We can 3D graphene. I definitely by the configuration of structure design, chemical design. So that give us many unique property. Not only keep this 2D electronic, the light surface area, mechanical property of 2D graphene, but offer many new functionality for structure and function application. So I think I'm stopping my talk here to give you the chance for the discussion. Thank you. Thank you. Mm-hmm.
Thank you so much, Professor Chen. Such a great talk. The floor is open for questions. Who's the first one?
Hey, Ankit, it's Krishna.
Hi. Yeah, go ahead, Krishna.
If no one else has, I just wanted to get the Professor Chen's comments on using wet chemistry processing to get porous 3D graphene structures.
I'm sorry, can you repeat? I have a little difficult to hear.
No, I was just curious, what your take on using graphene oxide, reduced graphene oxide systems to get a nanoporous or porous 3D graphene structures from wet chemistry methods or electrochemical methods.
That means you're trying to avoid the CVD growth, direct use graphene oxide to make the 3D plus graphene, is that right?
Yeah, that's my question. Like if CVD is very expensive to use.
But definitely, that's kind of the graphene oxide, reduced graphene oxide, basically much cheaper than CVD, right? For the large scale application, because you can make tons of the, the reduced graphene oxide, very cheaper, price compared to the CVD. So those, the people are working pretty hard, try to use it because it's cheaper. So you can easily to, get this material, you can construct in a 3D structure. But definitely, because this reduced graphene oxide itself is defective. So actually, you lost a lot of property of the graphene. But still, you compare to, the black carbon or those kind of amorphous carbon, the property is still good, right? But it's hard to, compare to the, you call that, I'm sometimes a little struggling to call those kind of material graphene because, it's the graphene not only has the thin atomic layer sample, but also need some unique property, right? So, for the commercial application, for certain kind of application, for example, work as a supercapacitor, or some the better applications, the price is important. There could be this material going to have a short future, but you really make some device application. You pursue some high-end application with retain the 2D electron property, probably CVD. We still need to stick on the CVD, even expensive, right? But the price basically how expensive or cheaper. The most case depends on the market value, the market size, right? But we are probably always the most important is property. If really some property we pursue is very high conductivity, we do need CVD. So probably in that kind of case, this reduced graphene oxide might not be a good competitor for the CVD growth 3D graphene. Is this the answer to your question?
Yeah, no, yes, I just wanted to get your perspective just because you.
Okay, thank you. But
yeah, so the next question is from Giali. Giali, can you unmute yourself and ask the question? Giali, are you there?
Yes.
Yeah, go ahead.
oh, I saw the question here, right?
Okay,
Can you
yeah.
make some culture without introduce a doping item, right? Is this your question? Yeah, the answer is yes. Because the
Yes.
doping, actually, the culture itself, we can grow this kind of pure graphene without any kind of doping. So that's actually, you see, I show a couple slides just for comparison. This is the basic material, fundamental material we use as reference. So because you have culture topological defect, more easy to do chemical doping, but that means you have to use chemical doping to keep the culture. Okay. So the answer is yes. Okay, thank you. Thank you for the question.
Thank you.
Yeah, Bruno, you're next.
Oh, all right. Thank you, Professor Chen. I enjoyed your talk very much. I have several questions, so I have some time with you after this. But one of them I think is interesting is at the time you're doing CVD, that's a pretty high temperature, right? So you should have thermal coarsening of your metal scaffold happening maybe at the same time that you are precipitating the graphene. And is there a competition in kinetics of those two processes at the same time, or one comes first, then the other comes? What's the competition there? Is there one?
Yeah, that's a pretty good question. Actually, it's true. So for narrow course metal, we can go high temperature CVD growth. For example, go to 1,000 degrees C. You make this even the nickel melting temperature is higher, but quickly this narrow course nickel get cost, right? You get larger pore size. So that's we have always looking for the kinetics, the balance point. The CVD temperature with with the quality of the CVD. So in our lab, we can grow the graphene as low as 500 degrees C and as high as 1100 degrees C. So that depends on your want. Basically, they tend to be this kinetic effect tend to be 1 power 2 for us to change the porosity, right? If we want small pore size, we want to the high density 3D graphene, we go low temperature CVD, right? So definitely need to be careful because low temperature somehow introduce more defect, right? So you have to optimize your precursor, optimize your growth condition. So actually, when you change this, combine, by the tuning this CVD temperature, you can tune pore size. So that's the reason I'm showing my slide. I can get 10 nanometer, 20 nanometer, very small, tiny small, the pore size graphene. I can get 1 micron, 2 micron, very large pore size. So I can do this kind of, the kinetic, the control for the subject. Or I can pre-annealing my nickel, or copper or nickel copper alloys, go high temperature, get, the 1, the micron, 2 micron porosity, right? I do CVD growth in the low temperature, right? So I can do this I can use this way to control the defect concentration. So I can use this very tiny small pool, I do fast heating, to go to high temperature, quick growth, right? Rapid quench. So I go high temperature, I still can get high temperature CVD growth, I get small pool size.
Wonderful, thank you. And do you expect the passivation layer, the graphene in this case, to suppress the adatom diffusion and thermal coarsening, or do you think it can still happen even with the graphene layer on top of it?
But that's a good question. So you presume I don't know. We didn't do this kind of research, but it's possible, right? It's possible. I cannot give you because I don't know. We have not tried to get the price is good. It's good. We need to think about that. Okay, thank you.
Thank you.
All right, Natalia, you're next.
Oh, hi there. I don't know if you guys can see me. Yeah, I was just curious about the whole trade-off process in terms of creating a layer that would be thick enough to have all of those benefits that were introduced at the beginning of your talk, and then also to create a part that's like dense enough so you would still keep the mechanical properties in there, but you also don't want to be too thick, because then you would have all of those challenges of, you know, the layers overlaying each other. So I just wanted to know if there's an optimum thickness and how that process of trade-offs take place in the dealloying process. Thank you.
Nanoprose nickel or graphene?
For both. I was
For both.
mostly curious about the graphene, but yes.
Yeah, definitely this kind of aspect ratio is important, particularly for graphene. I think for DLI, nanoprose nickel, nanoprose copper, it's not big concern. It's not big concern because they are pretty solid, right? So we know we are DLI sample, they are, you know, the self-standing, but only issue the residual stress and maybe cracking or something like that, right? But for the graphene, definitely the big issue because we make multiple size. Actually, atomic thing, you know, the what hard to hold it himself. Even graphene said the strongest material, right? But we talk about strength if you divide by cross-section area. That's actually not, that's, so that's the reason, that we cannot make a really large pool size with monolayer. Because those, the monolayer stuff, if we have the large pool size, they basically they're shaking by themselves, right? They're going to buckle. So actually, in our sample, in most cases, we control our pool size in the macron scale, well to macron.
In the macron scale.
In that case, so we still can get, I cannot say we are get pure monolayer, but at least, because the CVD curve surface, some area maybe get a couple, the multi-layer, or, the few layer, or some area, monolayer, but our Raman to the Raman survey, we notice, actually, if the pool size about 2 nanometer, is while to, the layer dominated graphene still can be self-supporting or self-standing. But definitely you go to people try, the people use the nickel form to grow tens of micron, this diameter porosity. Actually, after they allow the nickel, the sample simply crash, right? Because the pool size is large. The graphene cell cannot support itself. I think probably, I don't know, we need to do some theoretical calculation. It could be 1 to micron still okay for the monolayer graphene, but beyond that, it could be the issue. But when the pool size is smaller, it definitely starts to become more stable, right? So that's not a concern anymore.
I see. Well, thank you so much for your answers and your talk. Thank you.
Thank you.
All right. So maybe time for one more question. Maybe I can ask one. So yeah, great talk. I just had one question about, so I have seen recently a few papers that focused on how these ligaments form, and then they tend to also have hierarchical structures, which means they also have nanopores within the ligament. So have you tried any of the strategies to also replicate this for graphene?
You mean hierarchical?
Yes.
That's a good idea. That's a good idea. Basically, we never tried. We saw that before. Because actually, this for the last question, when you get a very large pool size, right?
Yeah.
Actually, this graphene cell is hard to self-standing. So if you get hierarchical, there could be, because each ligament going to be, still has a small pool inside. It could be self-standing. But we have never tried. That's actually the issue. I think maybe my student tried. I'm not sure. So the issue is, the cosmic, the kinetic. When you get hierarchical nanoprose nickel, right? Copper even worse, right?
Yeah.
When you go high temperature, CVD grows. You go high temperature, this small pool not stable, right? It quickly cosmic. So maybe now to keep this hierarchical, the porosity in the nickel substrate. But definitely go to try. It's actually this is pretty good. It's pretty good. It's pretty good. The comment. Thank you.
All right. Yeah. So yeah, we are close to the ending time. So Krishna, any final remarks before we close?
No. This was a great seminar. It was a perfect ending for our seminar series this fall. Yeah,
it was really nice. And yeah, and dealloying is one of the topics I've been trying to sort of do some phase field modeling on, but yeah, I'm still trying. So probably you'll see some papers in the future. Also, I think Bruno is the one who is doing a lot of that. Professor Sieratsky is not here today, but I'm sure he was going to watch the recording that we are going to post on YouTube. So thanks again for this great talk, and we are extremely honored to have you. Thank you.
Thank you.